So good morning, sir. Our topic of presentation is Raman spectroscopy. So before going on to topic, I would like to introduce my group members. My name is DHIREN, and my second member is Dayanand Meghwal, and my third member is Pradeep Daima. So in this PPT, we'll be first looking about the introduction of our topic, that is Raman spectroscopy, and then further we'll be looking at what is Raman spectroscopy, what we are more interested in this topic, and then the procedure involved in this technique, and then further we'll be looking at the instruments that we are using in this technique, and further that we will also look after the variation in Raman spectroscopy, and at last we'll look after the advantages and disadvantages of this technique. So starting with the introduction of this technique, so basically Raman spectroscopy was discovered by scientist C.V. Raman in 1928. It is a spectroscopic technique used to observe and determine vibration, rotational and other low frequency modes in system. So Raman spectroscopy is commonly used in chemistry to provide structural fingerprint by which molecule can be identified. So there are many other variations of Raman spectroscopy, including surface enhanced Raman spectroscopy, resonance Raman spectroscopy, micro Raman spectroscopy, and non-linear Raman spectroscopy. So let us talk about what is Raman spectroscopy. So in Raman spectroscopy, what we are more interested in this topic is basically when we pass an electromagnetic radiation through a molecule, most of the time the radiation just pass through it. Only some of the radiation will scatter, like it will go here and there in different direction. As we can see in this picture, that when we pass a monochromatic beam of a light, most of the light passes through the sample and some of the light scatters in different directions. So talking about scattering, so basically we have two different types of scattering. One is elastic scattering and another one is inelastic scattering. So firstly we'll talk about elastic scattering. What is elastic scattering? So when an electromagnetic radiation is passed through a molecule, let's say from ground vibrational state, it goes to a virtual state. So what is virtual state? Virtual state is basically an imaginary state which exists for a very short period of time. And from that virtual state, when the light comes back to our ground vibrational state, so it means that the energy of incident photon light is equal to the energy of scattered light. So when this condition exists, then we can say that the rays are elastic scattering, because the energy of incident light is same as the energy of scattered light. So this is called elastic scattering, or it is also known as Rayleigh scattering. So but this is not something we are looking for. We are more interested in inelastic scattering, because the principle of Raman spectroscopy is based on inelastic scattering. So let us know about inelastic scattering now. So talking about inelastic scattering, let's say when a beam of a light or electromagnetic radiation is passed through a molecule, let's say from ground vibrational state, it goes to some virtual state, and from virtual state, if it comes back to, let's say, first vibrational state, so we can say that like the incident photon light, the energy of incident photon light is higher as compared to the energy of a scattered light. So in this case, when the energy of the incident photon light is greater than the energy of a scattered light, then we say that this is inelastic scattering. It comes under inelastic scattering. This particular type of shift is known as Stokes shift. So now talking about anti-Stokes shift. So again, when we pass an electromagnetic radiation through a sample, let's say from first vibrational state, the incoming photon light, from first vibrational state, it goes to the virtual state, and it comes back when it comes back from virtual state, let's say it comes back to ground vibrational state. So here the energy of incident photon light is less than the energy of scattered photon. So when this case arises, like when the energy of incident photon light is less as compared to the scattered one, then we can say that it is an anti-Stokes shift. So here in this picture we can clearly see this. So moving further, this is the schematic representation of Raman spectroscopy. Basically, talking here, the very first step in this technique is that an electromagnetic radiation from an illuminated spot is collected using lens, and then from lens it is the rays are passed through beam splitter. So what does an beam splitter do? It splits the light into two, and some of the light is passed through some of the light is sent directly to the detector, and some of the light is sent to the sample. So after the rays which go from sample again gets back to the splitter, and they also goes to the detector part. So before detector, here what we have is a filter. What does a filter do? Basically, a filter filters all the elastic radiation from an inelastic source, inelastic radiations. So like basically it rejects all the Rayleigh scattering light from an inelastic scattering of light, and it only passes inelastic light to the detector, and we get the result. So now talking about instrumentation that we have used in this whole process. So basically there are three major components of Raman spectroscopy. So first is the light source that we are using. Second one is the filter, and third one is the detector. So firstly we'll talking about the light source. Basically laser are mainly used as light source in this method. So generally a shorter wavelength laser gives strong Raman scattering, because the intensity of Raman scattering varies as the fourth power of frequency. And here argon and krypton ions sources have advantage over the other source. So now let us look at some of the common sources, common laser sources. So argon ion can be used as a laser light source with a wavelength of 488 nanometer. Krypton can be used as a common laser light source with an wavelength of 530 nanometer, and helium neon can be used as a laser light source with an wavelength of 632.8 nanometer. So moving further, let us now talk about filter. So as we have seen, the work of filter is to filter all the Rayleigh scattering from inelastic scattering. Basically, in Raman spectroscopy, we use a notch filter to remove the light from the laser. So only the relevant Raman bands are present. Notch filter are basically a type of band stop filter and operate using the same principle. Notch filter have center frequency, which is the frequency that is the most attenuated. In other words, the center frequency is in the middle of stop band. So basically here notch filters are mainly used in Raman spectroscopy in order to collect high quality Raman spectra. So moving further, let us now talk about the detector that we are using in this method. So most commonly the photomultiplier tube is used as a detector in Raman spectroscopy method. So photomultiplier tubes are extremely sensitive detectors of light, and they are the member of class of vacuum tubes, more specifically vacuum phototube. These detectors multiply the current produced by the incident light by as much as 100 million times in multiple dynode stages. As we here we can see in this picture schematic representation of photomultiplier tube. So now talking about the working principle of photomultiplier tube. Photomultiplier are typically constructed with an evacuated glass housing. Basically, tight and durable glass to metal seal, like other vacuum tubes, containing a photocathode, several diodes, and at last there is an anode. So, incident photon strikes the photocathodic material, which is usually a thin vapor deposited conducting layer on the inside of entry window of the device. Electrons are ejected from the surface as a consequence of the photoelectric effect. So these electrons are directed by focusing electrode towards the electron multiplier, where electrons are multiplied by the process of secondary emission. The electron multiplier consists of number of electrodes called diodes. Each diode is held at more positive potential by 100 volt than the preceding one. A primary electron leaves the photocathode with the energy of incoming photon. A small group of primary electron is created by the arrival of a group of initial photon. The primary electron move towards the first diode because they are accelerated by the electric field. They each arrive with 100 electron volt kinetic energy imparted by potential difference. Upon striking the first diode, more low energy electron are emitted, and these electrons are in turn accelerated towards the second diode. The geometry of diode chain is such that a cascade occur with an exponentially increasing number of electron being produced at each stage. The last stage of this photomultiplier tube is called anode. This large number of electron reaching the anode result in sharp current pulse that is easily detectable. A small portion is inelastically scattered. This later portion is what we are particularly interested in because it contains the information in which we are interested. So now my second group member Dayanand Meghwal will tell you about the variations in Raman spectroscopy.
Uh, Good morning, sir. Sir, basically there are now more than 25 different type of Raman spectroscopy, and here we are going some special cases of the Raman spectroscopy variations. The first one is resonance Raman spectroscopy, which is used for study the free radical and biological materials. And now going to the second one, which is the surface enhanced Raman spectroscopy, SERS, basically which is the surface sensitive techniques, and gives us the direct identification of the target analytes or samples. And the third one, the micro Raman spectroscopy, which is used for identification of the different molecules present in the large molecules. In the fourth one, the non-linear Raman spectroscopy, which is basically tells about the which is based on the non-linear effects. So first, talk about the resonance Raman spectroscopy, which is used for the free radicals and biological materials. This type of the Raman spectroscopy refers to the phenomena which is means this type of the resonance spectroscopy. It enhances the Raman intensity lines with the factor of 10 to the power 2 to 10 to the power 3. The magnitude of the Raman peaks are greatly enhanced by the 10 to the power 2 to 10 to the power 6, and by this, because of enhancement of the Raman peak line, it can achieve the detection limit up to 10 to the power minus 8 molar. And also the basically, in resonance Raman spectroscopy, the wavelength of upcoming photons coincides with the electronic transition of the molecules. Means the electrons in the molecules are excited from one energy level to higher energy level, and by the electronic excitation of the molecule, there is a change in the structural of the molecule, and which reflected in the enhancement of the Raman scattering because of vibrational mode. And this vibration mode is undergo change in the bond length or force constant during the electronic excitation, and this can show the large increase in the polarizability, which measures how easily an electron cloud is disordered with the help of the electric field by using basically here we can see in the green one is the normal Raman spectroscopy, and the by using the resonance Raman spectroscopy, the virtual state are greatly Raman lines means Raman line intensity is greatly enhanced by the 10 to the power 2 to 10 to the power 6. And after that we are going to see the surface enhanced Raman spectroscopy, which is the basically the surface selectivity, truly on the surface selectivity effect. And in the surface enhanced Raman spectroscopy we are going to see that the surface here we can see that the we are using the surface basically the surface enhanced Raman spectroscopy can detect very low concentration of the sample because of the higher cross sectional area. By using normal Raman spectroscopy we can replace we can use the surface enhanced Raman spectroscopy, and it increase in the Raman cross sectional up to 15 order of the magnitude compared to the normal Raman scattering. And here we can see that the how our surface enhanced Raman spectroscopy is different from the normal Raman spectroscopy. In normal Raman spectroscopy we use only we use only the molecule given molecule, but in surface enhanced Raman spectroscopy there is a metallic nanostructural surface. Now after that we are going to study about the micro Raman spectroscopy. In the micro Raman spectroscopy we are using used for the identification of the different molecules and the functional group present in the larger molecule. In the micro spectroscopy what we will do is basically we replace the conventional number spectrometer by the micro Raman spectrometer. Because of micro Raman spectrometer contain a specifically designed Raman spectrometer, and in this spectroscopy we can detect a very small volume less than 1 micrometer in diameter, and the identification of the species present in the volume need the much lesser amount of the sample for the analysis. This amount of the sample is enough for analysis and doesn't require any sampling preparation. And after that we are seen the non-linear Raman spectroscopy, which is basically based on the non-linear effect. In this spectroscopy we are going to see the coherent anti-stock Raman scattering spectroscopy, which is known as the CARS. This is the based on the non-linear Raman technique that is used to enhance the Raman signals. Means this spectroscopy is also used for the enhancement of the Raman scattering compared to the normal, and it generates a signal with the frequency higher than the excitation frequency. And coherent anti-stock Raman scattering provides information about the intrinsic vibrational bond of the simple sample with the three-dimensional resolution. Now hereafter Pradeep will be continue.
Advantage of Raman spectroscopy. With the help of Raman spectroscopy, we can determine the sample in various states such like a solid, liquid, gas, crystal can be measured. It uses NIR laser light instead of visible laser light, which prevent photochemical damage to organic and biological particle during laser trapping and result. No sample preparation needed. Another advantage regarding instrumentation for Raman measurement is that focused laser beam can be used for both laser trapping and Raman spectroscopy. Now coming to the disadvantage of Raman spectroscopy. In Raman spectroscopy cannot be used for metal or alloys. The Raman effect is very weak, which leads to low sensitivity, making it difficult to measure low concentration of substance. This can be countered by using one of the alternative technique, resonance Raman, which increase the effect. Now coming to the applications. With the help of Raman spectra, we can analyze homonuclear molecule, example H2, N2, O2 very accurately. Triatomic molecule, for example H2O, SO2, NO2, CO2, etc. can be studied by Raman spectra and structural nature of the molecule. Raman spectroscopy is also useful in nanotechnology to understand the structure of nanowire purification of carbon nanotubes. Because of their structure, carbon nanotubes can be made to resonate with the light. With the help of Raman spectroscopy can be used to measure stress and strain in materials. Tensile strain increase the length of the bond and the tension in them. We can also measure the structure in carbon material sp2 and sp3 structure.
This was all about our PPT. Thank you for your patience.